Hello, Math 1342 students. This is extra practice for Quiz 7. Quiz 7 covers mass, center of mass, and work when we have variable force, say. And so we get started with number 1. This is a mass question. We have a thin wire, and it lies between x equals 1 and x equals 3 with density delta of x is natural log of 2x. Find the mass. Well, we just integrate. So what we want here is an integral from 1 to 3 of the density, ln of 2x dx. Now the question is, how do we integrate this function? Well, ask yourself, do you know off the top of your head a rule for an antiderivative for a natural log? Not really, right? And so this is one that is by parts. It's a great practice of integration by parts. So if we recall our integration by parts, well, all we have is a log. And so that is our u. We have the L in Leaky. So our u is ln of 2x. And dv, well, dv is everything else except the integral sign. Here it's just dx. And you can check, if you take u times dv, we have the whole integral except the integral sign. So this is great. Now, differentiate u, and we integrate on this side. If you integrate 1 dx, you have x. Over here, there's a few ways to think about the derivative of this function. If you think, say, chain rule, it would be 1 over 2x times 2. You notice this is just 1 over x. That's one way to think about the derivative of ln 2x. Then integration by parts goes uv minus the integral of v du, but it's definite. So you have to remember it's definite. Okay, we have x ln 2x. And then we evaluate between 1 and 3. And then minus the integral from 1 to 3. Here's where it will be v du. This would be x over x dx. Okay, which I can simplify. Maybe I will. This first term, though, I can go ahead and evaluate. This is 3 ln 6 minus 1 ln 2. And then we subtract off the integral from 1 to 3 of just 1 dx. Now we're almost there. This is 3 ln 6 minus ln 2. And then we have minus x evaluated between 1 and 3. Here we have 3 minus 1. And so my final answer is 3 ln 6 minus ln 2 minus 2. This is the mass of this wire. Next one, we have a metal plate, and it occupies a region between x squared minus x to the 4th and x squared minus 1. We're told the plate has density cosine of pi x over 4. And this is set up only, so we want to find an integral that calculates the total mass and find integrals that calculate the x and y coordinates of the center of mass. Okay, well, we need to first figure out the x values where our region lives between. And so we can set the curves equal. X squared minus x to the 4th equals x squared minus 1. Then you notice, what do I get from here? I get x to the 4th equals 1. And we have two solutions to this. We have x is 1 and negative 1. Okay, now, you can certainly graph the region in your graphing calculator, but what we really need to know is which function is the upper and which function is the lower. And you can do that by, say, evaluating at something in the middle here. So for instance, at 0, what do we have? Well, this first one is 0, and this one is negative 1. And so that tells us x squared minus x to the 4th is bigger than or equal to x squared minus 1 on this entire closed interval, which is minus 1 to 1. This will help me set up the right integrals. So part A, we want the total mass of the plate. Well, we integrate minus 1 to 1. And to get the mass, we take density, which is cosine pi x over 4. And then times upper minus lower. And we figured out what this is. The upper function is here. And then subtract off the lower. Now, maybe because this appears in so many intervals, I will take a step to simplify this because we will see this in the integrals in part B as well. So we have minus 1 to 1. We have cosine pi x over 4. And then we have x squared minus x squared is 0. We have just 1 minus x to the 4th. 1 minus x to the 4th. That is upper minus lower, where I have just collected the like terms. So this is my mass, my integral that calculates the mass. Now we move on. We need y bar and we need x bar. Okay, maybe x bar is the shorter one, so we will do this first. We take 1 over m, 1 over the mass, and then we integrate minus 1 to 1. You see, a lot of this stays the same. We will still have density. We will still have upper minus lower. And of course, it's an integral. We'll still have dx. So I'm just copying and pasting that here. But then for x bar, we integrate x times all of this. Okay. You have 1 over m, the integral minus 1 to 1, x times density, upper minus lower, dx. This is the answer for the x coordinate of the center of mass. Now the y coordinate is a little bit different. Well, some of it is the same. We will still have 1 over m, 1 over the mass. We will still have an integral, minus 1 to 1, and we will still have this part, density, upper minus lower, dx. But then instead of x times all of that, we will have 1/2. And then we have the sum of sort of the two curves. So if this is, say, f and g, it would be the sum, f plus t. So what is the sum here? Well, I have x squared minus x to the 4th plus x squared minus 1. Now I could certainly write that as 2x squared minus x to the 4th minus 1, but it's perfectly fine like this. I think I'll just leave it like that. So this is the answer to number 2, setup only. We move on to number 3. We have a tank, and it's the shape of an upside down right circular cone, vertex pointing down, circular base at the top. Let's start drawing. This will help us. So if I start drawing part of, okay, here's a triangle. Now let's see if we can make a cone. Okay, I think that is reasonable looking. Here is my right circular cone. Now let's start labeling things. So I always put 0 at the bottom, whether my vertex is pointing up or whether my vertex is pointing down, because this is how my world is oriented. It's what makes the most sense to me. So here's 0. Now we are told the height is 50 meters. I can put this here. We're also told the base radius is 40 meters. So I can put 40 here. And then it's filled to a height of 30 meters. So let's find 30. Say maybe it is here. Here's 30. And then I have some liquid. Now, one thing we see as we read this problem is we are in metric. Okay, that is important to know. So here's my liquid up to a height of 30. Let's write down all of our formulas. We know that work is force times distance. We know that force is mass times acceleration, and mass is density times volume. So let's figure out, well, first let me slice. Okay, so we have some slice. Thickness delta y, and the slice is sitting at some height y. Okay, and my slice has its own radius. Maybe I'll make that pink. We have some r. Okay, let's figure out the work for my slice. And I'll check my units here, make sure I have everything. In the end, this is metric. My units of work are joules. So we begin here and kind of work our way up. First, we start with density. This is 900. And this would be kilograms per meter cubed. Then I can multiply by volume. Well, this is pi r squared times delta y, and this is meters cubed. So you see, just like we should have, we have kilograms, which is a unit of mass. Now, multiply by gravity. Acceleration due to gravity is 9.8 meters per second squared. So now you notice we have kilogram meters per second squared. This is a Newton. And the final thing is I need to multiply by a distance. So my slice is sitting here at height y, and I want to pump the liquid to the top, okay, which is here. Oh. Okay, to pump to the top of the tank, right here. This distance is 50 minus y. So that is what goes here, 50 minus y. And this is in meters. And you notice altogether, we have joules here. So we have the correct units for work. Now, the only thing before I can write down my integral is here. I do not have r as a function of y. And to do this, I need similar triangles. So let me just kind of recopy this triangle over here. We have, this is 40. We have, this is r. We have down here, this part is y. And then the total height, this is 50. Okay, so we see that r over y equals, well, 40 over 50. And to get r as a function of y, just multiply through by y. We have r is 4y over 5. This is writing r as a function of y. This is what I needed to finish getting this just in terms of y. But I think I'll go ahead and write down my integral. So we have an integral. All of this I write down, except instead of writing r, I will write 4y over 5. Okay, then we have 9.8, and then we have 50 minus y. And then when we go from sort of Riemann sum notation to integral notation, this delta y, it's really in the limit, becomes dy. The final thing is my limits of integration here and here. You see, we integrate over where my liquid is, and my liquid lives between here and here, 0 to 30. So I integrate 0 to 30. And this is my final answer. Maybe I'll write my units here. This is in joules. This was number 3. Number 4, this is our leaky bucket question. My sand is green in the picture. Okay, so we have a bucket, and initially it weighs 50 pounds, and that's here at the bottom at 0. And we want to lift it up here to 100 feet. And then we are given information about how fast it's traveling, a constant rate. We are given information about how fast it is leaking, constant rate. And then we want to set up an integral to find the total work to lift the bucket 100 feet. So this is work with variable force here. And what I need, let's write what I need. I need an integral. We would integrate 0 to 100, the force function. I need to write this as a function of y. Say my height, dy, okay? But I don't have that function. I need to figure it out. So what are we given? F of y will be the force at height y. And we are given enough information to determine this. We are given dy dt equals, it's being lifted up at 5 feet per second. We are also given the sand is leaking at a constant rate, but this is leaking at a rate with respect to time. So we are also given df dt is, it's leaking. So this will be minus 0.2. This is pounds per second. We are also given more. So we are given here, number 1, we are given number 2, and we are given the initial force, right? Because force is in pounds. So we are given at height 0, we have 50 pounds. Well, there's a few ways you can do this problem. I'm going to do it kind of in a Calc 1 way for this video. What I need is df dy, because I want my function as a function of y. And if you recall, this really comes from the chain rule. This would be df dt divided by dy dt. And all of these rates of change are constant. And so my rate of change with respect to y will also be constant. So let us just divide. This would be minus 0.2 divided by 5. And you can check the units here, right? Up here, we have pounds per second. And then in the denominator, we have feet per second. Altogether, we would have pounds per foot. And that's what I'm looking for, because I want the rate of change of the force with respect to y. Y is in feet. Well, this is negative 1/5 over 5, which is minus 1 over 25. I can also write as a decimal as minus 0.04, but it's fine like this. Now, what functions have constant rate of change? These are our lines. And so, well, we have calculated the m. This is the slope of my line. And we also were given initially the b. This is the b. Maybe I should highlight these. This is the intercept. This is the slope. And so I just need to write this in my integral. We integrate 0 to 100. Here we have m, which is minus 1 over 25, times y plus b, which is 50, dy. This would be my final answer. Of course, this is not hard to integrate, but that's not the goal here. We're trying to set up an integral that calculates the work. Now, just as a comment, this is in US customary, and so this would be foot-pounds. Okay, this is number 4. Now, our final one, number 5, is the spring. We may assume Hooke's law applies. We are given a spring, and we're told it has a natural length of 4 feet. This length is 4 feet. But this is the x equals 0 because it's its natural length. And we're also told 21 pounds of force is required to hold it stretched 7 feet. And then we want to calculate the work. So we have to understand or read the question carefully when we're given a work problem with springs, because Hooke's law says the force, f of x, is kx, where k bigger than 0 is the spring constant. This is the force required to hold a spring stretched or compressed x units from the equilibrium. So here we are told we have 21 pounds of force, and then we want to calculate a work. A work, just like we saw in the last example, will be an integral of this variable force. But I need to convert these lengths to x values where 4 feet is x equals 0, is equilibrium. Well, 7 feet would correspond to x equals 3. And then the other thing we see is 5 feet. This would correspond to x equals 1. Okay, this is in sort of units past equilibrium feet, of course. Okay, now I have everything I need to do this problem. We are given 21 pounds of force is required to hold it stretched 3 feet past equilibrium. This is what we are told. And so this says my spring constant is 7. We want the work required to stretch the spring from 5 to 7 feet, which is from 1 to 3 past equilibrium. And this would be kx dx. So we have 7x squared over 2. And we evaluate between 1 and 3. This gives us 7 times 9, which is 63, minus 7 times 1 divided by 2. This is 56 over 2, or 28. And again, we are in US customary here. And so this is foot-pounds. So this is the end of this question. And this is the end of quiz, let's see, 7 extra practice. Thank you so much. Good luck on the quiz.